In this video, we're going to discuss question 11 from Practice Exam 3.1 in the fall 2021 semester in Chem 1211. And this is a really interesting question that combines an understanding of electron configurations and how to go from an electron configuration to an element on the periodic table, and periodic trends. And periodic trends are going to come in with respect to electron affinity. So the problem mentions electron affinity. And so we're going to be concerned with that in this problem, and in particular how it varies across the periodic table after we've identified each of these elements. So there's more than meets the eye to this problem. There's a little bit under the surface. One thing we can notice immediately, though, seeing that every electron configuration given has the core of Ne, is that we're dealing with elements in the third row of the periodic table. We're dealing with elements whose valence shell is n equals 3. And so I'm not going to look anywhere else on the periodic table than the third row in order to start identifying these elements. And let's go ahead and try to think through the elements by laying down A through D here, A, B, C, D, E, and I'll be looking at the configurations from the top to the bottom. We want to identify element symbols for the elements just to make our lives easier. So let's pull up the periodic table here, and we're going to bounce back and forth between the configurations and the periodic table to figure out what we're looking at. So first configuration is 3s2, 3p1. We're going to start at sodium, that's 3s1, 3s2, and 3p1 gets us to aluminum. So the first element there is Al, or aluminum. 3s2, 3p4. Well, now I'm at 3p1, 2, 3, and 4. That is sulfur. The third choice, 3s2, 3p3. Well, that's just one step back to the left of sulfur. That is phosphorus. We've got 3s2, 3p2, which is silicon. And last but not least, we have 3s1, which we actually previously identified as sodium. Now, we're interested in the element that has the most negative electron affinity. So this is the most exothermic electron affinity. A way to put this in the language of the process that's going on is the most favorable electron capture. Most favorable electron capture. So remember, electron affinity refers to this process by which a neutral atom, let's call it X, in the gas phase, captures an electron, takes an electron from kind of oblivion, as I like to say, and forms an anion, X minus, in the gas phase. The most favorable electron capture is what we're looking for here. And you can get to this a number of different ways. You can think about electronegativity trends. You can think about effective nuclear charge. If we've got the periodic trend in electron affinity on a crib sheet or somewhere, the easiest thing to do is look at that. So since I have the luxury of showing this on p-table, and this is something you can have on your crib sheet in terms of how electron affinity tends to vary, if I turn it on, we can see pretty clearly that the most exothermic, now these are positive values, but the positive values refer to exothermic electron affinity, which is a bit confusing given the problem says most negative, but bear with me here. Electron affinity is exothermic, except for the extreme exceptions like the noble gases. And among the elements we looked at, which include aluminum, silicon, phosphorus, and sulfur and sodium, the most negative electron affinity is associated with sulfur. And this makes sense. Sulfur is the most electronegative element among this series. It's also has the highest electronegativity among the elements in the series, and so it's going to most favorably capture an electron. Its capture of an electron will be the most exothermic process. In essence, this is two ways of saying the same thing. To loop back really quickly to the problem, the electron configuration that corresponded to sulfur was neon 3s2, 3p4. So there's your answer right there.